Okay, I can see many of our attendees are joining. Um, so good morning, good afternoon, wherever you are joining us from. Welcome. So on behalf of UK High-Rise and GW Shift, it's my great pleasure to welcome you to today's joint seminar on exploring Asia's hydrogen revolution. My name is Mi Tian, professor at the University of Bath, and I'm delighted to be chairing today's webinar. The webinar will last 1 hour with around 45 to 50 minutes for the presentation. And hopefully we have short 5 minutes time for questions. So the session will be recorded, so please keep your microphone muted during the talk. You're welcome to post questions in chat at any time. If we don't have time to address all of them during the session, we will respond afterwards and post the answers on our website. So I'll start with a short overview of GW Shift and UK High-Rise for those who may be new to our programs. Can we have the next slide, please? Okay, GW Shift is the Great Western Supercluster of hydrogen impact for future technology. It's an EPSRC-funded initiative connecting academic, industry, and civic partners across two countries, Southwest England and South Wales. It aims to accelerate the development of a regional green hydrogen ecosystem. Next slide, please. UK High-Rise, on the other hand, is the national hub, the UK hub for research challenges in hydrogen and alternative liquid fuels. It's a 5-year, over 10 million EPSRC-funded national research hub led by the University of Bath. It brings together partners across the UK to drive research and innovation across the whole hydrogen value chain, from production, storage, and end use and system integration. So with that context, it's my great pleasure to introduce our speaker today, Professor Haiwen Li from Sun Yat-sen University. Haiwen has hold academic position in Japan and China, and is internationally recognized for his work on advanced materials for hydrogen storage and batteries. He has published a significant amount of papers and serves as an expert on hydrogen storage within the International Energy Agency. So making him ideally placed to speak on today's topic. Haiwen, thank you for joining us. And if you are ready, could you please share your slides?
Okay, thank you very much, Lee, for your kind introduction. Let me show my slide. Okay. Can you see my slide?
Yes, we can see your slides perfectly, and we can hear you, and the floor is yours.
Okay, thank you very much. Let me show here. Okay. So again, thank you very much for me and also for your kind invitation for this great opportunity to say into some activities about hydrogen energy in Asia and also some of my own opinion as well. So again, I'm Haiwen Li from Sun Yat-sen University. So I emphasize here Shenzhen. In the beginning, I briefly introduce where we are. So now I'm here. So somehow, if you see this map is off this side. Now here is just 8 p.m. I think we have 8 hours time difference. So we are here, and our city is Shenzhen. So this is Shenzhen campus of this Sun Yat-sen University. So to University bus somehow it's 10 hours flight, and our university basically this year is the 102nd year. So it's founded in 1924. we have almost 60,000 students, and we have 5 campuses. So our Shenzhen campus is one of the newest campus. So this is the Shenzhen city. So our campus is here is at the north part of this Shenzhen city. So this campus was officially put into use in August 2020. So that means almost 5.5 years ago. And here we have 17 schools, almost 17,000 students. So you can, from this map, you can see, so our campus is neighbor to Hong Kong, so it's very close to Hong Kong. By high-speed train from Shenzhen to Hong Kong, it's only 14 minutes. Today, I would like to take this opportunity to introduce 3 parts. Firstly, I would like to focus on the Asian energy consumption and competition. Then I would like to introduce national or somehow regional hydrogen strategies. In the last part, I will introduce the recent activity, especially on the technical demonstration of metal hybrids. So basically, I think Professor me and myself, somehow we are working on this field of the metal hybrid. As you know well, so one of the important background is carbon neutral goals. Most countries have this goal by 2050, and some countries are 2060. So UK is here, so China is here. I think the most important background is energy security. So I think this figure, although the data is not very new, but I think it showed very interesting information. If you see here, so this figure shows the production indicator for oil and for gas. For example, for the Asia and for the Europe. So there's no data showing here for UK, but anyways, I think we have a similar situation. I mean, uh, basically, so we have to import a lot of oil and also gas. That's a basic situation. So uh, on the other hand, one of the solutions is the renewable. For example, if you see this wind power density potential, even though the density is not so evenly distributed, but I think the distribution is much better than the oil and gas. A similar thing happened for the solar panels, solar energies. So this means the UV increase the ratio of the renewable energy. That means that we can somehow reach the goal of this the seventh goal of this SDGs. I mean, there's a target to reach 17.5% of the renewable energy. This map shows the data a little old. I mean, between 2010 to 2018. The green color means the ratio of this renewable energy is increasing. But I think nowadays the green color would be much more than before. That means anyway, so to utilize the renewable energy, that's a very important solution for energy security. You will see the current situation of this world energy supply by source. Currently, for example, you will see the last 30 years, basically, we are relying on the fossil fuels. For example, this is the coal, oil, and the gas. And also here we have the biofuel and waste, and nuclear, and electricity and heat. Somehow this related to the renewable energies. Basically, you can see more than 80% we are relying on the fossil fuels. You will see this energy supply by region. You can see United States is here. Somehow the amount is a little reducing, and if you see the Europe, you can see almost a constant, but a little somehow reducing. But there's a big increment you can find from the Asia. For example, here this is 1990s. So this is the China. This is Asia, except for China. So in total, you can see Asia, the increment of the energy consumption increases quite, I would say, significantly, so very fast in the last 3 decades. And you will come to Asian to see the energy consumption. So it's a similar situation to the global trend. But the apparent increment is this from this somehow renewable related part. So you see this renewable energy production, I would say, since especially after 2000, I mean, when we enter into this century, so the increment became significant of the renewable energy. You will see the Asian renewable energy production by region. So this is also interesting figure. So the red color is South Korea. So this is ASEAN, the green one. So the pink one is Japan. So this light blue is India. So this blue is China. So you can see clearly. So the China had invested a lot on these renewable energies. And from the future forecast, it is predicted for example, you will see the future till 2050, the major energy or power generation is from the renewables, especially from the solar and the wind. That's a future forecast for China. And you will see the renewable electricity in the major countries in the last 3 decades. For example, for the hydropower, you can see China also increased a lot for the wind. So this is the blue one in China. This is the yellow one in the US. So this is Germany. And for the solar, also this is China, the US, and Japan. But for the total renewables, clearly, so in the last 20 or 30 years, so China had invested a lot on the renewables, especially for solar and wind energies. But as you know very well, the renewable energies, especially for wind and solar, they have two big issues. The first thing is either wind energy or solar energy, the power generation does not match with the demand. And another issue is this upper limit or this acceptance capacity of the power grid. So because of this situation, you can see here, so for example, for many countries, especially for example, for some projects in China, even though you install many solar or wind mill for this energy production, but you can see because all this acceptance limit. So you have to face this problem or this technical curtailment. So this means so how to utilize the renewable energy. That's a key issue. I think you know the answer. So hydrogen is one of the important carrier which can connect with the renewable energy to the end users. The important role of hydrogen not only can be the clean energy carrier, also, hydrogen are the industrial feedstock. So that means so this is a very, very important role of hydrogen. So this is so the slide I emphasize why hydrogen is so important for the global, for the many countries. And such background, I would say globally, many country or many region, they announce their own hydrogen strategies. For example, from this map, you can see so far over 60 nations have announced their national level hydrogen strategies. So from this map, you can see this is a global event. This means that the hydrogen is very important. And you will see this order of the year. So Japan is the first country announced the hydrogen strategy in 2017. So especially after 2019, you can see the significant increment of this national hydrogen strategies. Uh, so firstly, let me explain the situation in Japan. So again, so Japan is the first country announced the hydrogen strategy. So they announced this strategy just after the Christmas in 2017. For this, from this scenario, you can see there are a lot of data about, for example, the hydrogen volume, the cost, and the application. But in short, basically, I think it can be divided into two parts. So the first part, how to scale up the hydrogen supply. I mean the hydrogen capacity and also the how to reduce the cost of this hydrogen supply part. And another important part is the utility. So how to use hydrogen. For example, you can use hydrogen for the power generation, and also you can use hydrogen for the mobility, for example, for the fuel cell vehicles, the fuel cell buses, and forklift, and also some other application. So in Japan, it's called any farm. It's kind of residential. It's a small scale and power generation system. So I will explain it later. To realize such scenario, Japan they planned the three phases. So, for example, in the first phase, there are two important products because this is a first phase, so it need time to uh, penetrate the product into the market and also to increase the public acceptance. The one of the product is this so-called NFM system. This is a cogeneration system. Uh, Cogeneration means the cogeneration of power and heat by the fuel cell system. This is used for residence. And another one is this fuel cell vehicle. In phase two, mainly focuses on the power generation. So here, I mean, relatively large scale power generation for the pure hydrogen combustion power generation system. So this is 1 megawatt system. Another one is using the solid oxide fuel cell. It works at a high temperature around 800 to 1000 degrees C. So this is in Japan. It is in 2016 in Kyushu University campus. It is the first large system. Is 250 kilowatt working on the solid oxide fuel cell for power generation. So it can cover 30% of the electricity of this campus. So I worked for 10 years. And in phase three, so in phase one and phase two, so there's no mention about the so-called color of the hydrogen. But in phase three, aiming at a realization of this zero carbon emission hydrogen society, that means the green hydrogen society. That's three phases in Japan. In 2023, Japanese government revised this strategy. So firstly, they set the new targets. One thing is the hydrogen introduction. So here, the hydrogen including the ammonia. So you can see this number is quite a large number, 12 million tons in 2040. That means trying to scale up the hydrogen amount. And another point is the electrolysis capacity. So here, this number, 15 gigawatts, this means the Japanese company they produce the electrolyzers and it is used not only inside Japan, also including it is used in other countries. So this means this is target in 2030 in global. And another point is, as I mentioned in the last slide, so at this stage, so the government trying to promote the transition to low carbon hydrogen, somehow the so-called green hydrogen. So sets the low carbon target for hydrogen and ammonia, and also establish the regulation for about this low carbon hydrogen. The third target is support scheme to build large-scale supply chains. Uh, because in Japan, as I mentioned in the beginning, so they don't have enough. I would say basically they have to import almost all the oil and the gas, and also for renewable energy. Also, they are not very rich. So that means they have to consider how to import large scale hydrogen, how to build the large scale hydrogen supply chain. That's quite important. Uh, for realizing the real hydrogen society. So this means you need a lot investment. For example, here it is a number 15 trillion Japanese yen in the next 15 years. Also, they mentioned to strengthen the industrial competitiveness. For example, it has five parts. For example, the first one, again, you have to consider hydrogen supply, including the hydrogen production and also the supply chain. And the second part is decarbonize the power generation and the fuel cells, and also the direct use of hydrogen. So here, it means include the hydrogen as a feedstock, for example, for steel, for the chemical product, and also for the hydrogen fuel vessels as a energy carrier, and also utilization of hydrogen derivatives for them for the fuel ammonia. So fuel ammonia means ammonia combustion to generate power, and also carbon recycled products. This is this is carbon recycled. This is somehow ammonia based application, and also another one is the realized safe hydrogen use. So here show the kind of somehow brief conclusion of this demonstration in Japan. The data is a little old, but I think it covers the main achievements for the hydrogen mobility. Firstly, the hydrogen station network in Japan. I think that now it has almost 170 hydrogen refilling stations, and also they have this. Joint venture. So based on the different companies, because before the first 100 hydrogen refilling station, it was totally supported by the government. From the 101st hydrogen refilling station, it is built by this joint venture, and they have different applications for the vehicles, for the bus, for the vehicles, and also for truck and the train. Also they have the fuel cell ship. I think another important project is this local and regional projects, because one of the difficult point for hydrogen is storage and the transport. So if you can produce hydrogen locally and use it locally, I think that will help a lot. So again, local production, local consumption, I think that could be one of the important way to use hydrogen. From that point, for example, Fukushima, they have the nuclear plant accident in 2011, March 11th. So when I was in Sendai, in Tohoku University. So anyway, so at this area, because the people, it's difficult to live there, and they are trying to somehow use this land to put more solar panels to generate the renewable energies, and also creating the hydrogen hubs in different areas. Again, as I mentioned in the last slide, because Japan had to consider how to make sure, how to guarantee the stable and large scale and low cost hydrogen supply. So they have the demonstration projects. For example, one is between Japan and Brunei, because Brunei has gas, so they're trying to use low cost gas to produce low-cost hydrogen by steam reforming reaction. And then this hydrogen is stored by this liquid organic. So here they are using toluene to then by using the chemical tanker to transport hydrogen to Japan. That's one of the demonstration operated by the chemical industry. Another one is between Japan and Australia. So because in this area or Australia, they have the Bronco. So Bronco is a coal, somehow a relatively young coal. They have a lot of water inside. If you use so from the point of fuel as a coal, so it's not a good coal, but it can be used for the gasification to produce low cost hydrogen. And then this hydrogen will be liquefied. So this the Japanese company they use the liquefied hydrogen carrier, use this ship to carry hydrogen to Japan. That's another project. Indeed, there's another project. It's not shown here. For example, they have the project between Japan and UAE. They're trying to use to import ammonia from the Middle East. And for the power generation, one of the large scale power generation, there's a combustion. So this company, for example, Mitsubishi Power, they succeeded the demonstration in 2018 in Kobe City for the 1 megawatt pure hydrogen combustion. And also, the fuel cell also it has its advantage, for example, for the from the small scale to the large scale of the power generation. Okay, so then let's move to South Korea. South Korea also they are very interesting in this hydrogen. For example, they have the vision to become the world first top class country in hydrogen economy. So they announced this strategy in 2019. Also, they have a lot of numbers. Basically, I would say this is similar situation with Japan, so you have to consider the hydrogen supply and also the hydrogen application. I think one of the most important events in South Korea is this one, is they passed the world's first hydrogen law. So in 2020. So this is very important. This law came into effect in 2021. So this is a big push for the hydrogen application in South Korea. Also from their first master plan, they included many detailed points. I would say similar to Japan, for example, firstly, they are thinking so how to lead domestic and overseas clean hydrogen production. So this is a very important part for this is the base, I would say, for hydrogen society. And then build a nationwide infrastructure. So how to supply hydrogen in the whole country. And then use hydrogen in the daily life and also strengthen the hydrogen ecosystem. So because we don't have enough time to speak detail, but in 2021, South Korea, they recorded the world's highest growth rate. There are several interesting points. For example, in 2021, the cumulative supply of the fuel cell vehicles in Korea is 19,000. So it is at that time is world number one. And then the fuel cell power generation capacity also at that time is the largest in the world. The number of the hydrogen filling stations in 2021, it was 170. Also, it was the world number one. Okay. Then I would like to shift to China. In China, the government policy it determined the development direction for many important events. You will see this figure. So there is a turning point. So this year is 2019. So you will see this world hydrogen strategies. You can see also the big increment started from 2019. So that's a very perfect overlap. So in China, issued the fourth national level hydrogen plan. So that's a 15-year plan in 2022. Uh, from this plan, so we have several targets. For example, by 2025, so we have this number for fuel cell vehicles, 50,000, and the hydrogen, green hydrogen production. By the way, current situation, I think now we have in total 30 something thousands of the fuel cell vehicles. And for green hydrogen production amount, that's I think that's 125,000 tons per year. Somehow this number is almost somehow reached to the minimum, but the fuel cell vehicle number still somehow not reach this goal. But anyway, I think that's a big improvement in China. And in 2030, so the target is to realize a relatively complete hydrogen industry. And in 2035, so a comprehensive hydrogen industry. So I would like to mention here, so supporting the energy transition. I think the point is before 2035, I think that the most, especially here, the important point or important role of hydrogen is for industrial application. I mean, as a feedstock. Uh, to realize such goal, so different province in China announced different targets. So I don't talk in detail. But there is an interesting analysis of the hydrogen energy development potential for cities in China. So it is divided into four groups. So you can see here you have several parameters. You have supply, you have demand, you have the policy environment. So you see this yellow or gold color. So this almost 70 cities, they have somehow high potential for hydrogen energy demand, supply, and also policy environment. I would say if you check the city, the most cities, they are rich city in China. But anyway, because this is a new technology and also, this is a very long industry chain from the hydrogen production, transport, storage, and also application. So you have to consider the investment. And also, the second group is somehow policy guided. And for these cities, the third group, they have potential, but mainly rely on the market forces. I mean, they need more time for hydrogen. And this the last group, they need somehow, because this area, I would say they have low population, somehow, for the market, they need a much longer time. Anyway, to realize such a hydrogen strategic goal, so the hydrogen demand by sector in China, so it's shown here. Currently, in China, we have 30, I think it is 36 million tons of hydrogen production per year. And if we want to realize the hydrogen strategic goal in 2060, the number of the hydrogen uh, must reach to 100 to 130 million tons. So this means you need a lot of, say, increment of the hydrogen production. Currently, especially for green hydrogen production, basically rely on the electrolysis. So this means so we have to develop renewable hydrogen capacity. So this 100 gigawatt scenario means in 2030, so we have this 100 gigawatt target. In 2060, the number will reach to 500 to 750 gigawatt. So that means that there is a huge increment of this green hydrogen production. Uh, this means I think we need a lot of electrolysis system to produce the green hydrogen. So under such background, So, for example, we have a lot of demonstration for the green hydrogen product, green hydrogen production. For example, this is the largest project. It begins in 2023. The initial output of the green hydrogen production is 10,000 tons per year. So the finally it will reach 20,000 tons per year. So this is a very large scale of this green hydrogen production. This hydrogen is used for the refining. And another important project is a green ammonia project. Also, it's called the world's largest green ammonia production project. This project is under construction. From this information, you can see it will have 700 megawatts windmill, 100 megawatts solar energy, and it will produce 180,000 tons per year of the green ammonia. And so here, the electrolysis capacity is here. So per hour, it will produce 46,000 normal cubic meters. And for hydrogen storage, so this product, they are using metal hydride system. The capacity is 5.4 tons. I think for a metal hydride system, this is the largest one currently. So this is the photo, this metal hydride system for the hydrogen storage. And another very important event in China is this one, the first energy law. So officially enforced last year, so 2025. And it's the first time the hydrogen is integrated into the energy system. Because before this energy law, hydrogen is classified as a hazardous chemical, because if you put this level on this hydrogen, then there's a lot of barriers for the application of hydrogen. So this is a very important event for the hydrogen application in China. Okay, so here shows the national green hydrogen mission in India. So they announced this in 2022. Basically, so they have three targets. Demand creation, so by making green hydrogen, so produced in India. And the second one is addressing supply side, and also building an enabling ecosystem. For example, they announced the expected outcomes of this mission by 2030. So here is a green hydrogen production. So 5 million tons per year. And also the renewable energy capacity is 125 gigawatts. So anyway, so this is the data for India. Also, from different areas, they have this different states. They have their own targets to promote the hydrogen economy. So here shows the timeline of the release of this hydrogen strategies released by the ASEAN member states. For example, this is Singapore 2022, 2023 Philippines and Malaysia, and 23 Indonesia, and 24 Vietnam. So they announced the short term and the middle term and the long term roadmap. Basically, they are a little somewhat behind, but anyway, they are also trying to improve the hydrogen and the ammonia future. For example, for the short term, they will establish this ASEAN alliance and also attract private investments. And so focus on hydrogen deployment in I would say it's here is for industrial application, for the chemical as feedstocks. and also establish standard for the hydrogen and ammonia handling. And for middle term, so ramp up low carbon hydrogen and ammonia production, and then they will shift the focus from this industrial application to the transport and power generation. And in the long term, so regional trading and use hydrogen for process heat, and also finally they want to establish hydrogen as a building block for energy security. Okay, so far I briefly introduced the hydrogen strategies in Asian countries. Then I would like to explain the technical demonstration of metal hydride. This is the chain of the hydrogen economy, so production, transport, and use. But I would say the hydrogen storage and transport is crucial. We have several ways to store hydrogen. For example, you can use the compressed hydrogen, that means the high pressure hydrogen. Of course, so you have the issue of the volumetric hydrogen density. This is quite low, and the safety measure, and you can use the liquid hydrogen. So, this boiling point is very low, and the liquefaction efficiency is low, and also you have the boil off evaporation problem, and you can use the liquid organic hydride like toluene, ammonia, and also you can use the solid. For example, typically the solid state hydride, I mean the alloy or inorganic material. But anyway, for each method, so it has its advantage and disadvantage. So I would like to emphasize here is there is no one method which can cover all the applications. So I mean, you have to consider based on your application, and also in some cases, you have to combine them together. So here I would like to emphasize a little why hydrogen storage is very challenging, because this the character of the gas. This figure shows the compressibility factor as a function of the pressure, so at 300 Kelvin. So I mean, if this number there, if it is larger than one, that means this gas its gas is hard to compress. You see hydrogen here. So hydrogen is very difficult to compress. If you reduce temperature, you can see here only when the temperature is as low as 50 Kelvin, and only at this very narrow pressure window, I mean below 120 bar, so hydrogen became easily to be compressed. That means because it's character of this gas or hydrogen, so it's very difficult to compress hydrogen. It means if you want to store more hydrogen in the same space using high pressure, you have to increase the pressure. Then anyway, so because of this character, so it's very difficult to compress hydrogen to a small volume, and also you have to consider the safety measure for the high pressure hydrogen. Another point is, for the gas, sometimes you can use it in the liquid phase, but for hydrogen, if you check this phase diagram, so this critical point is also very low, the only 33 Kelvin. That means if you want to liquefy hydrogen, you have to reduce the temperature below this temperature. So this means the hydrogen also is hard to liquefy. So the liquefied process is very energy consuming process. And also, again, because the boiling point is only 20 Kelvin, so you have this vapor loss issue of this liquefied hydrogen. And so here I have the comparison of the hydrogen storage technologies. Taking an example, this fuel cell vehicle Mirai from Toyota, this is the first generation. If you want to drive 600 kilometers, you need 12 kilogram of hydrogen. So if you use gasoline, somewhere around 50 liters, but for hydrogen, it's a huge volume. At standard conditions, 56,000 liters. So Toyota, they succeeded in using the high pressure hydrogen. So this is a 700 bar. high pressure, so the inner volume of the tank can be reduced to 122 liters. And if you use liquefied hydrogen at this extremely low temperature, 20 Kelvin, the volume can be further reduced to 80 liters. But if you use the hydrogen solid material, I mean the hydrogen solid alloys, it can work at the temperature below 30 bars, even 10 bars, and it can work at around room temperature, and the volume can be further reduced. So again, for this, if you consider this somehow volumetric density, so the hydrogen storage material has several advantages. Is for example low pressure, high safety, high density, small volume, and also quite simple operation. For the solid state hydride, basically it can be divided into two groups. So one group is called the interstellar hydride. So in these compounds, so hydrogen occupies the interstellar space among the atoms. And it forms the metallic bond. On the other hand, for the non-interstellar hydrides, by the way, the interstellar hydrides, they are comprised of the transition metal. That means they are quite heavy because the metal they have very high density. So that means that the gravimetric density of these interstellar hydrides, in most cases, they are below 380%. But for non-interstellar hydrides, you can see they are comprised of the light elements, but they will form the quite stable covalent or ionic bond. This means many compounds they release hydrogen is higher temperature. I mean about 150 degrees C in some cases. For example, for magnesium hydride, it requires even about 300 degrees C. But anyway, so far, we have a lot demonstrations based on the metal hydrides. For example, from the stationary application to mobile application, and the scale can be several grams to tons of the hydrogen storage. Briefly, it can be divided into four groups. For example, mobility, delivery, stationary compression. So I don't have enough time. I have run a little. So for the mobility application, because as I mentioned, the hydrogen storage alloys, they are quite heavy. But for example, for the forklift and also for the ship, because they have the limited space, the hydrogen storage alloys, it has the highest hydrogen volumetric density. And also for both cases, they need a weight balance and also they are safe. So I think these two uh, are big potential for solid state hydrogen storage application. Also in China, we have this demonstration to use the metal hydride system for the refrigerated truck. And also in China, we have the shared bicycles and the scooters. So in the last 2 years, it was told we have even several 10,000 of these shared bicycles and scooters on the road using the metal hydride system. For delivery, so for this part, I think Japan, there are many demonstrations because in Japan, according to the high pressure law, if the hydrogen gas at 30 degrees C, the pressure is about 10 bar. So you have to apply for the high pressure gas law. Metal hydride system, you can design the pressure below 10 bar. That means you do not apply for this high pressure law. So in Japan, basically the system are below 10 bar. By using such low pressure and safe system, for them, hydrogen can be delivered with a lifeline, and also for example in Hokkaido, so far the heating basically using the oil burning. But in the future, they are trying to use the fuel cell system to provide power and heat together. So in such case, so the low pressure hydrogen, that's one of the safest and also feasible way to distribute hydrogen. And also for them, for the outdoor activities, if you have a fuel cell, you have this tank, so the low pressure tank, so you can supply power. So in China, we have another kind of demonstration for the hydrogen transportation because you know for the hydrogen trailer, based on the 200 bars, it can only carry 200 to 300 kilograms of hydrogen. That's quite a small amount. By using this magnetic-based system, you can transport almost 1 ton of hydrogen. But because magnetic system, it works at quite high temperature. So for them, 300 degrees C, you need such heat resource for both sides. For this stationary application, I think this is one of the important applications for the solid state hydrogen systems. So, for example, in Japan, there are the demonstration for the season shift or the solar energy in this hotel. I mean on the roof there are the solar panels. They integrated with the hydrogen system. It can supply the electricity for the whole year of the two buildings, and also it supplies the hot water. Another important point I would like to emphasize is here. Siemens Corporation is the top three construction company in Japan. In their new building in 2021, they put the hydrogen storage solid state system underground. So at the basement, they use it for the backup of power. And also there's demonstration for large scale of the green hydrogen storage. Here is almost 320 kilogram of hydrogen. Again, in China for the green ammonia production, also there's a large scale, so 5.4 tons of the hydrogen. And also there's a compression application. The point is this is quiet and also low pressure, quiet and also no vibration. That can be used in special cases. So in Japan, also in China, we have such kind of demonstration. Only use the heat below 80 degrees C. Okay, before ending my talk, briefly, 2 minutes, my university. So this is the broad view of my university, the Shenzhen campus. And this is the main gate, and we are here. So we started the energy storage group in 2024 in August. So we are focusing on energy storage for hydrogen storage and also battery from material to system integration. Also, we have positions for PhD and postdoc and also for the associate professors. So Shenzhen, again, this city, I think you must visit in China because it has only 40 years history, and it's a home to global giants and also this springboard for startups for AI, robotics, green energy, and also so we have a lot of beautiful architecture, and also we have a lot of green parks. So we have 1,350 green parks. Anyway, so that's a beautiful city. This is the last slide. Uh, Indeed, last year, we started to organize the international symposium focusing on hydrogen and energy storage. So this is a homepage, and also we will continue. We plan to do this year, maybe in November or December, but we will decide soon. So you are welcome to visit us, and also if you have any questions, also you are welcome to reach me by this email. So okay, I remain 6 minutes. So thank you very much for your kind attention.
Thank you, Heaven. Thank you so much for the excellent and insightful presentation. I'm particularly pleased to hear your point that local hydrogen system can be more efficient and cost effective, and that aligns closely with the vision of GW Shift, where we are looking to accelerate the regional hydrogen supercluster. And also the demonstration projects you showed us are particularly inspiring as well. Unfortunately, we are running out of time, but I believe the conversation will continue afterwards. Before we close, I just want to highlight a few upcoming seminars and ways to get involved with GW Shift. Karen, are you there? Could you please share the information? And I saw the questions are coming up, and we will collecting all the questions from the audience, and we'll forward to Professor Lee, and then post the answers on our website afterwards. Because of the time, I'm a bit conscious, and I like to highlight a few upcoming events. One is the Fueling Regional Girls taking place on 13th of March, and supporting early career researchers in hydrogen and sustainable energy research commercialization taking place on 25th of March. And the past seminars can be found from our website's resources as well. And thank you very much for joining. Thank you everyone for joining our today's seminar. We look forward to seeing you at future events, and continuing this important conversation. Thank you and have a good weekend. Bye.